Okay. Hello, welcome to M Paper Club. Today I'm going to present the paper that is behind DALI 2. And my name is Vahan, if you don't know me. I'm back presenting. And today, paper, I'm going to start sharing my screen so we can actually look at the paper. Let's do this. Can you see the screen? All good? Is it big enough?
Yep.
Okay, great. So the paper is called Hierarchical Text Conditional Image Generation with Clip Latents. The name is a bit long, but we'll cover all components of that. The bottom line is this is an improvement from the clip latents model, but using the clip embeddings combined with priors. So let's actually go straight to the. Actually, let's look here. The idea is that we are generating images from a given caption, right? We all have seen these models during the last few years, but this one is actually very interesting. The idea is that you give a caption like vibrant portrait painting of Salvador Dali with a robotic half face, and then you get an image that captures that. We'll talk about limitations because this doesn't always work so nicely, but in many cases it does. And if you go down, you can talk about the architecture from the beginning, actually, the high-level architecture, then we'll go into details. This should give us an idea of how the model works, what are the main contributions here. We'll talk about related work at the end, if there is time, because, well, in the paper it's at the end, but also we want to cover the paper first, and then as we do it, we'll also talk about related work. So in this diagram, above the dotted line, we have the original clip version, where we have this model with clip embeddings, and the C in clip stands for contrastive. We'll see what the contrastive part is here. But the idea is that you give pairs of images and their captions. So each pair is an image and a caption, right? And then the model learns an embedding that represents both the caption and the image. Right? This is important, and it helps a lot for many downstream applications. Contrastive, it's called contrastive because the objective is basically saying learn the embedding in a way that if it's the same caption and the same image, maximize their similarity. If they are different, minimize. Right? In every given batch, we have these pairs, which is why it's called contrastive, and there is no actual label. Right. What we have in this new paper is first we use the clip embeddings here, and they are fixed. Okay. And then there is this prior bit, and we will investigate two sorts of priors. The one above is the diffusion prior. The one below is the autoregressive prior. We'll go into details for this later. And then there is this decoder part, which basically takes an embedding and then generates an image from the decoder. So before we would have an inverted encoder that again takes an embedding and generates an image. Here we just have this prior bit and the decoder is also different. Any comments here about the high-level architecture? Anything we should cover before going into details?
Are you going to go over what a clip embedding is?
Yes, briefly. Actually, I wanted to show the paper, but now I lost it. The clip embedding is basically the result of training this contrastive objective. And then as you train that, you end up with an embedding, which represents both the caption and the image, right? And that was used for DALL-E also. And the idea is, well, it's an embedding that represents both. That's all.
I thought that the embedding was only an image embedding, like the image, that it wasn't, and it was just like a really effective image embedding.
Yes, it is the image embedding, but you can also, but you find that embedding while training with the captions, right? So it also embeds the caption. It's not sorry. Okay. It's not a word embedding, obviously, but it also represents the caption.
Okay.
Right?
It's actually quite cool that these two are in the same space, right? But
yeah, that's the important thing. Yes, the caption and the image are represented in the same latent space. Those are the clip embeddings. Cool. Let's go a bit down. There are a few important terms here. The diffusion models, right? DALL-E and Glide. We will compare with those. And our model is also similar to this with some modifications. So we'll cover those. And the other thing that that's important is, let me find it here. Right. This new architecture is called unclip, stack of unclip. Unclip because, well, it goes the other direction from clip. They basically take the clip embedding and then generate the image out of that. So it's the reverse. Was there a comment? Or... okay. Now, the method, right? It has two main parts: the prior, which produces the clip image embeddings, conditioned on the captions, right? That's the prior part, as we saw up here. And then we'll look at two possible priors. And then there is the decoder, which takes the which generates the image X, given the image encodings and the captions.
One question: in the decoding part, is the prior sampled from?
The prior sampled from.
Yeah. So we encode, we get this an encoding vector, and then on the way outwards, is the prior there to sample from it essentially, or?
Well, it produces a new embedding, right? But yes, by sampling.
Yeah, probably. Yeah. So that's must be non-deterministic, I think.
Yes, that's not deterministic. Okay. But the clip embeddings are fixed.
Yes.
Right. That's important.
The blue one is fixed, right? The blue one is fixed, but the
orange one.
No, the prior goes straight from the text, right?
What do you mean?
If you scroll down again, I think it said the prior is a function of the embedding by the input caption, right? So
prior produces the clip image embeddings conditioned on captions. So it takes the caption as input and produces the clip embeddings.
So that is by itself also an encoder, right? Yeah. It yes. Encodes Y to be Z I.
Yes.
Yeah. So I was just trying to wrap my head around it.
Yeah. So these are VAE models, right? There is the encoder decoder parts, but it's a bit more complicated than a simple VAE. We can go into more details about what sort of VAs work here best, but that's more like prior work. Okay, the decoder part. It's mostly based on the decoder described in the glide architecture, glide model. And the main part is that it's trained in a way that it can be reversed, right? Because there is a special training here that it can be reversed, but also there is this image super resolution part, which is also quite cool. So they have two image upsampling models, two separate ones. I don't know why they choose these specific upsampling models, but they have two. One uses a Gaussian blur to upsample, and then the other one is a PSR degradation, which I don't know what it is. If anyone knows, feel free to comment. I didn't check the references here, but the point is, there are.
Can you show me where it says it? I just want to see.
PSR degradation.
And we use a more diverse BSR. I don't know. Okay.
Right. So basically, they take the smaller image from 64, and then they upsample it to 1024, 1024. That's basically to make the model more computationally efficient. But at the end, we will see that this also causes some limitations, because this also limits the generated image quality. But it's a more efficient way of training models. They also say that they only use special convolutions for the image upsampling, and there is no tension here. They do use transformers later, but for a different purpose. Another important thing about the decoder is that they enable this classified free guidance. So this is used in, again, taken from prior work, and it's a common technique. But the idea is that they randomly set the clip embeddings to 0 during training 10% of the time. So this basically removes the clip embeddings 10% of the time, and also randomly drop the text captions 50% of the training time, during training. So this is to improve diversity of the models, of the generated images. Sorry. That's another important concept here. It's taken again from this other work, which we may want to cover at some point during Paper Club. I checked, we didn't cover this before. Quite interesting work, actually. Okay, anything about decoder, or should we go to the prior? Let's talk about the prior then. So they cover two sorts of priors, autoregressive prior, which basically goes through multiple steps, multiple stages of sequences of creating discrete codes, and those are done autoregressively, so using the previous steps. And then there is the diffusion prior, which uses a Gaussian diffusion model. But I should just tell now that diffusion priors work better. We'll see in the experiments later. And what else is important here? Oh, another interesting thing here. So with they actually use a PCA to reduce the clip embedding dimensions. So for some reason, if they use SAM, which is a training, which is an optimization method, if they use this optimization method to train clip embeddings, the embeddings actually end up with a very low rank. So they are able to perform PCA and reduce the dimensions from 1024 to 319, and without losing much or any information, which I found was very interesting. They do this with they do this with autoregressive priors, which helps with the computational efficiency, obviously. But then but after that, they also quantize these dimensions into the original discrete buckets. I didn't really understand why they do that. It's probably to maintain the architecture dimensions, right? I don't see any better reason for that. Those are the two main things about the priors, and the loss functions for the priors. This part gets a little bit technical, but they also here they actually talk about how the clip embeddings are trained also, because it's really similar, right? The idea is that, as I said, it's contrastive learning, which means maybe I can draw it somewhere. No, I can't. So if you put the if you may imagine a matrix with images on one side and then the caption on the other dimension, and you want to maximize the dot product on the diagonal, not on the diagonal, the dot product on the diagonal, and then minimize on everywhere else, because you want to if you want to because you want to match the two embeddings so they end up in the same space. That's where the dot products come in. And loss function is the squared error, mean squared error. Any comments here? No. Because this paper is more about taking techniques from many places, so there is not a lot of technical detail here. But yeah, go ahead, Alex.
Do they use actually sequences of stuff? I didn't quite get that step.
What do you mean sequences?
When you have these causal attention masks on sequence. Yeah. At what point do we have actually a sequence, right? Because it's image to image or image to image.
Oh yeah. I skipped that part. I should skip
the diffusion training, but yeah, my memory is a bit bad. I know we had a paper about it, but not quite sure how that works.
So they used the same transformer from the attentional unique paper. At least that's what they cite when they say transformer. And then they put this causal attention mask on a sequence that they construct. Right? The sequence is here. If you look here, the encoded text, the clip embedding, an embedding for diffusion time step, noise clip image embedding, and the final embedding, whose output from the transformer is used to predict the unnoised clip embedding. Right. So there is the sequence, and then they mask that sequence. Right. And then, which is usually how you would train a transformer. And it's a decoder transformer.
So that is still part of the diffusion step, essentially.
Yes, that's the prior. How do you mean diffusion step?
Yeah. Oh, wait, we trained that, right? Because the prior has to be trained. And that was, I think I barely remember, but you noise it and try to let it train what was the original, right? And then step by step, yeah.
Yeah. Oh, there is another interesting thing. So they also say we choose not to condition the diffusion prior on the dot product between the two embeddings, like in the autoregressive prior, which is what they normally would do. But here they managed to improve quality during sampling time by generating two samples of Zi and then selecting the one with higher dot product. This seems very ad hoc, but it works, right? And then they also don't add any noise that also to the Zi. I haven't read this other paper, but they say they don't, which is supposed to be standard thing, but they decided to not add noise to that eyes because, again, it just worked better.
I have a feeling that maybe at OpenAI they have like a set of guidelines for what works best for autoregressive models and what works best for diffusion models, and so that's how these techniques were like determined. Because even if you read their language modeling papers, you get the same impression. They just have like a lot of techniques that they use that are kind of heuristics that seem to improve different types of models when you have a massive data set.
So I guess also pretty much every paper they cite that I checked is from OpenAI. So they could also go ask the authors. So what should we do? Right? They are in the same organization. Maybe they are also some of them are the same authors. So it's a bit of insider information. Anyway, we can look at these images with some interesting examples here. Actually, this is actually interesting because they show that what you can do is when you take two embeddings and you actually, let's go step by step. So they discuss creating variations in these images, right? For example, so figure 3, you go back here. There are lots of images here, so let's be careful. They say, so if you take an image by encoding with clip and then decode with the diffusion model, okay, the variations preserve both semantic information like presence of a clock, as well as stylistic elements, right? So that's actually good, right? So it's not the same image, but it preserves the important information, which is a good feature of the clip embeddings. Same on the right side. This is to understand the model components better. So that's about the variations in the clip embeddings. The other one, which I found more interesting down here, interpolations. So if you can blend two images for creating variations. And they do that by using this spherical interpolation. And the theta is a parameter of weighting parameter between the two embeddings, right? So if you look here, for example, this is the image, right? You can take the leftmost image, well, it's given here, and then the dog is here, and then, well, you can combine them, interpolate them, you playing with the theta parameter. As you can see, as you go from left to right, images change. Right? So that's another property of the embeddings.
It's not smooth, right? Or is it that that I can take any step in between and the image would be smaller and smaller and smaller?
What do you mean smooth? It's a continuous variable, right? Theta is a continuous variable.
Exactly, but if I move the embedding by a very small value, it looks like the pictures themselves still change quite drastically. Like the position of the dog doesn't seem to be like continuous, but it could be wrong. It could be just because it's very rough grain.
I mean, yeah. I mean, visually, I guess no, but I'm not sure how to define smoothness, right? If you
like that the image generated becomes arbitrarily close when the embeddings are arbitrarily close, right? And I don't know what
is continuous.
Yes.
I think a better question is how cherry-picked are these sequences? Like, how many images did they generate at different interpolation points? And like, did they literally just choose this? Is this like just a single sequence, or is this like stitched together to make a good sequence, like a sequence look good?
Hard to say, but they do talk about limitations at the end. So these are, we can call it cherry picked, but they choose the good ones here and then the bad ones later, right?
Yeah, I have no problem with cherry picking in a paper to show good results, because they still are able to do this with their model, even if they have to like do some human filtering.
Yeah. Same with the other example, right? If you have a continuous, not continuous, but some uh, change between two images.
Yeah. Again, here, especially where we have these topologies involved, but it's not clear whether you can smoothly interpolate between them, or do you just have some, I don't know how to call it, semantic interpolation between them.
It also depends on the two images, right? Look at the lines here.
Yeah.
Because these are very similarly positioned lines. It looks like the line is just aging. Right? This one, it looks a lot smoother.
Yeah,
So
yeah.
I guess it depends on the case. Now that's the text differences. Oh, so here is the comment we mentioned before, that because clip embeds images and text to the same latent space, that means they can also take the caption and interpolate between the captions, right? So these are done using the captions. The first example was with images. The second one is with the captions, which may be why it's kind of smoother, because the image is generated from the caption and then interpolated. Cool. Any more comments? No? Okay, now probing the clip latent space. So this is another example of studying the embeddings generated in this with this model. There is an interesting problem that seems to be solved in a surprising way here. So if you have a photo of an apple, right, and then you put an image on it, put text on it, usually these clip embeddings don't work well, because they actually take the text from the image instead of the actual apple behind. But somehow, even though the probability of the decoder, no, the predicted probabilities being incorrect. So, for example, if you only have the Granny Smith apple, its probability is perfectly right. But if you put the iPod on it or pizza on it, everything gets wrong. Actually, if you put iPod, it's wrong, right? But pizza seems to be better. But those are the predicted probabilities. But somehow the decoder still generates a meaningful image from this, which is surprising, right? Because it's classified as incorrectly, but generates the right image, which may also be not surprising, because I guess if you give the generated image, it will also be classified incorrectly. So the latent space represents this apple as iPod, right? But it also generates it correctly. So I guess it makes sense.
Where does this classifier actually sit? Is that it's not part of the regular model, right? It's something that's essentially added on top and trained.
Yes, it's just later, right? So once you have the embeddings, then you can have a classifier, which is how these models are often tested for zero-shot setting.
So it's probably that classifier itself that is botched up somehow.
Yes, but even though the classifier, oh, you mean because they are separate, because the classifier may be wrong, but the decoder is still right.
And you still sort of would have to know what the classifier is trained on then, and it looks like the classifier is generalizing wrongly from the embedding space rather than the embedding space being bad.
Yeah, I guess, yeah. But is the classifier separate then?
It must be, right?
Oh, there's the tag. Yeah, so this is about the tagging, right? So this is designed to get the wrong answer.
Yeah, probably I don't know enough about clip, but so clip by itself can also predict labels, it seems, right?
But you need to define labels. You need to give it to a classifier.
Also, so you have to give it the labels, and it adds the probabilities to those labels then.
Yes.
Okay.
I think so.
I mean, you could argue that for a classifier, the iPod is not a bad label, right? To be attacking to, so that actually says iPod, right? So it just looks almost more like an objective mismatch than anything else here.
Yes. Yeah. Could be. Yeah. But anyway, the point is that the model is still able to generate relevant images. That's the point I want to make. Even though it's even though it's not safe against those sort of attacks, as you said, Arvid, it's not really an attack then. Maybe the generated images are still meaningful. I guess some of them are. Like this one is a bit weird. Right. Also, you can notice here that the generated text actually doesn't make much sense. We'll look at those later at limitations. But this model is not good at all when it comes to generating text in the image. Right. What else do we have down here? All right. So, yeah, comment.
So with the classification, so they've kind of just had very
no comment.
Given that this method can take complex text.
I think Pierre, your microphone might be
off.
Very, very hard to hear you, mate. Maybe type it in the chat.
Hello, Piero?
I'm going to try and type it in text.
We can hear you now. Well, maybe keep doing this.
Okay, fine. Okay, right. So the question I have is that if you go back to the classification task, so I can see to some degree why it's got iPod there, but what this clip algorithm seems to do, the previous one, with the Granny Smiths, can it take an image and then produce complex text from that? So we try and encode more than just simple nouns, right? We want meaning, context, etc. And it seems here they're just using something very simple to interpret these images. I was just wondering if they'd tried to say take a complex painting and try and extract some kind of semantic meaning from that rather than just a label for classification. Does that make sense? So, for example, for the Granny Smiths, they would say it's a Granny Smith's apple on a table in a garden with a fence, that kind of thing. You go from the image to the text, but not just
you can
Granny
do that.
Smith.
So that's what you can do. Yes, there are other models that can generate text from the image. ChatGPT 4, this new one, does that actually. But you can give an image and get the caption out. You can also generate a caption, yes. No, not with this architecture, because this one generates an image, but you can use the same embedding structures to also generate text.
Yeah, I suppose the question I'm asking, when you look at the architecture, will that function, will that architecture ever be reversible, where you can take an image and then it can use a series of, clip embeddings and some idea of the diffusion process and say, actually, I think this image can be interpreted this way. I think that would be interesting, but nothing beyond that.
Yeah, I'm pretty sure you can do that, and there are papers doing that. So if you go up to the architecture, yeah, going a bit slowly, but okay, we got there. So basically, here you want the decoder to generate a caption instead of a text, instead of an image, right?
Yeah, that's it. Yeah.
Which you surely can do, but you will need a different decoder, obviously. And there are other papers that do that.
Okay.
But the clip embeddings will remain the same, I think. Okay. Thanks for the question, the comment. Let's go down to here. We were up here, I think. All right, here. So here they also investigate the importance of or the impact of the PCA dimensions. They also, so basically they try with different PCA, different number of principal components from 20 to 320. And on the left, you have the lowest number of principal components. On the right, you have the highest number. And all those images make sense, right, with their captions. But the interesting thing is that with a higher number of principal components, you get more details, right? Which I found very interesting. So as a reminder, the PCA is done on the clip embeddings. So you put all the clip embeddings stack after each other, make a matrix, and then do PCA, reduce the embedding dimensions. So the more you reduce the dimension, the less detail you get on all examples, which is very interesting. I found. Cool. Now that text to image generation parts. Now the question is, how important is the prior? Well, actually, it's not strictly necessary for caption to image generation, but actually you can remove the prior and then it becomes the glide model. But it helps to create more diverse images when we generate them. That's the important part for the prior. And then we will also compare between the two priors, so the autoregressive and diffusion options. If you go down here, so here we have the each column represents a different caption, and we part down with three different methods. Right, first one is only using the caption, so the rest are passed as zeros. The second one is as the caption with the text embedding, and then we have also the image embedding from clip. As you can see, well, as we go down, the results get better, right? What I noticed here is that usually, if you only have the caption, somehow only the first part is taken into account. So it's like an oil painting, you just get an oil painting, right? Or maybe not the first part, but one part. Here it only takes the shoe. It's not able to capture even the entire caption, which I found interesting. Right. And then the next, actually, the evaluation metrics are right. The next evaluation metric is comparing using human evaluations. Right. Besides looking at the standard numbers, they also look at how do humans grade each one of those models, and they compare three models. Glide, that's the one from Dolly, and then the new arm clip with two priors. So if this number is less than 50%, then Glide is preferred by humans. If it's more, then the new model is preferred. Okay. So first, diffusion is always better. Diffusion prior is always better. The other is, in terms of photorealism, numbers are very similar, but still, Glide is still a bit better. Caption similarity, Glide is still a bit better, but only slightly. But when it comes to diversity, here we are generating much more diverse images, which is a good thing. So that the two measure diversity, I think they give a 4x4 grid of generated images for the same caption, and then they ask the human to grade which one is better. Actually, they just ask which one is better. Okay. All right. There is another interesting thing. So they are saying, okay, so what happens if we reduce or increase their guidance scale. So this guidance is a technique that that's used for all these image generation models, and that's basically a way to control for. Well, there is a paper for it, but the paper describes it as a method to improve computational efficiency, but achieve same results in terms of generation quality. Basically, what we notice here is that, as I said, above 50% means unclip is better, right? What we notice is that we can actually play with this guidance scale, and as the guidance gets less, the quality of unclip generated by the quality of images generated by unclip improve, whereas glide decreases a lot. So glide depends a lot on the guidance, having this guidance parameter. Same with it's the same thing, but a different measure. Let's actually look more. Right, so next performance metric is for zero-shot training. Right, so we trained the model taking images and captions from the internet. Oh, there's a good question, right? How do you find those images and captions? Well, Instagram, anywhere on the internet, which is basically a lot of freely labeled data. Now, and then they take the trained model and compare it on known data sets. So this one is a standard data set used for image generative model performance measures. And as you can see, well, first of all, unclip is a new state of the art in terms of zero-shot learning. Obviously, there are a couple of other methods that are trained on the same data set that do a bit better, but these are zero-shot, which means they have not been trained on the same data set. Cool. Any comments here? Okay. Oh, aesthetic quality. They are arguing that guidance improves aesthetic quality for both models, both glide and unclip. It's in figure 13. I think it's this one. Oh, it's 12. Right. So they also measure it here. So basically, as you increase guidance, aesthetic quality gets better for all models. However, this recall, which is the opposite metric, gets worse as the prediction quality improves for the glide model. So there is a trade-off for glide, but apparently not so much for the unclipped models. I think that's all. Let's have a quick look. Oh, those are just examples from the tested data set that we mentioned before. This is all for the paper. We can talk a bit more about the related work because this builds a lot on related work, but any comments, questions first? No?
Nope.
Well, the main related work is, well, this, first of all, VQ-VAs. So that's a approach for training VAs, but that's a lot more efficient and better. Maybe we can cover this paper at some point during a paper club, but that's also not very new. The other important remark here. Peter, do you have a comment or can I meet you? Office is very noisy. Sorry. But if you want to talk, it's fine. We can wait. No? Okay. The other important work is clip, obviously, because it was all about clip embeddings. And they also mentioned GANs, but GANs don't seem to be state of the art anymore for the last few years now. Now limitations. This is actually important. I didn't mention limitations. So they also mentioned that when you have a description combining two objects from two different styles, then the model struggles, right? For example, here, if you say a red cube on top of a blue cube, model starts struggling because it doesn't really understand which word relates to which word. And that's a limitation of clip embeddings. The other interesting limitation was, well, this is also similar. Again, if you try to reconstruct images with multiple objects in the prompt, then the model starts struggling. The other one is text. So this model obviously does not understand grammar. So when you try to generate text in the image, it doesn't make much sense. Again, known limitation of image generation models. And the other one, this one is levelless of detail. Right? If you try to generate a very complex scene, level of detail from unclip is usually worse. Right? Like you can see the dog here is very realistic, almost like Photoshop. From unclip doesn't look as good. Same with the New York picture. Right? It's not great for generating images with high complexity. And I think that's all for the paper. Any comments, questions?
Nope.
None from me.
Thanks for attending. Thanks, Piero.
Actually, I do have a question. Sorry, I had a problem with my mic again. You come across these papers. Can you hear me?
Yes.
Yeah. So you come across these papers. I mean, very interesting. But I had a quick scan of the paper. I'm not sure there is any like source code or repositories where we can actually look at the architecture. It seems like this is a method. We've done something. There's some data. Trust us. That kind of thing going on. And I'm not questioning the authors or the method. I was just wondering, are you aware of any kind of code repos where we could look at like example implementations or anything like that? And I could have missed it in the paper, but.
Very good question, but that's a general problem with OpenAI. Ever since they changed their business model from OpenAI to making profit, they don't publish code or models anymore. If you want open source models, there are some. Hugging Face usually trains similar or the same models and makes them open source, public. There are other models from other corporations or universities that may not be as good, but they are open source.
And Peter, this is to your ChatGPT. This is going to be really odd. Have you guys ever tried to take like a paper and ask ChatGPT to produce code off the back of it?
Nope.
Okay. No, because I've done that with some simple architectures, and it does produce like high-level TensorFlow code. Oh yes, this is how you implement this this model. Whether the code's correct, I haven't got to that point yet. But you know, sometimes you just can't be bothered to re-implement known architectures. Like, well, actually, there's this paper. Look at this text. Give me the code. That kind of thing. And I think in this case, it probably wouldn't work. But maybe more well-known architectures or variations, it may work better. I don't know. I was just curious because when I look at papers, I'm interested in code. I'm interested in, okay, show me a GitHub repo that I can go and actually check it out and run the code so I can test it. I can kick the tires, maybe even your data if that's available. And again, it's not a criticism. I understand they have a business model, but at the same time, there's a lot of trust, right? And I'm a coder, so I want to see code, right? I want to kick the tires and understand what they're saying.
I should correct
Sorry?
myself here. I should correct myself here because they do make some models available. So DALI, I think this is the first one Peter just shared in the chat, right? The first DALI, the architecture is, but not the training model, I think. But the DALI should be public also, right?
Well, DALI
Okay.
2, they have a repo in OpenAI, but it's called DALI 2 Preview. So maybe they'll release it at some point in the future. I think they're just going to release the code for the model, though. They don't release the data, so you can't really train it. But I don't even know if you would be able to, unless you're like a massive organization anyway, because of the size of the data sets they train on and like the amount of compute they have available.
Yeah. Also, publishing the model architecture code doesn't actually give away anything extra because it's all in the paper, right? Having the data and trained models is of more value, which is not available.
Yeah, I suppose, but it shouldn't be so data dependent. If you've got your own. Well, anyway, it's a discussion for another time, maybe. But yeah, okay, yeah. But thanks for that link, Peter. I'll definitely have a look.
Cool. Thanks all.
Thanks, Vahan.
Thanks, everyone. Cheers.
Very good. Speak
See you
soon.
next
Bye-bye.
week.